Okay. Okay, so we need to go back to the mass transfer. Okay. All right. I mean, this is ridiculous.
Last video, I left you with a puzzle. The setup involves 2 sliding blocks in a perfectly idealized world where there's no friction and all collisions are perfectly elastic, meaning no energy is lost. One block is sent towards another smaller one, which starts off stationary, and there's a wall behind it, so that the smaller block bounces back and forth until it redirects. Sometimes math and physics conspire in ways that just feel too good to be true. Let's play a strange sort of mathematical croquet. We're going to have 2 sliding blocks and a wall. The first block starts by coming in at some velocity from the right, while the second one starts out stationary. Being overly idealistic physicists, let's assume that there's no friction and all of the collisions are perfectly elastic, which means no energy is lost. The astute among you might complain that such collisions would make no sound, but your goal here is going to be to count how many collisions take place. So, in slight conflict with that assumption, I want to leave a little clack sound to better draw your attention to that count. The simplest case is when both blocks have the same mass. The first block hits the second, transferring all of its momentum. Then the second one bounces off the wall, and then transfers all of its momentum back to the first, which then sails off towards infinity. 3 total clacks. What about if the first block was 100 times the mass of the second one? I promise I will explain to you all the relevant physics in due course. It's not entirely obvious how you would predict the dynamics here, but in the spirit of getting to the punchline, let's watch what happens. The second one will keep breakout. Very rapidly at one point, adding up in all to 313 total collisions. Well, actually, hang on. Wait for it. Wait for it. Okay, 314 clacks. If the first block was 1 million times the mass of the other, then again, with all of our crazy idealistic conditions, almost all of the clacks happen in one big burst, this time resulting in a total. Though it's forgivable if you don't, since it defies all expectations. And published in 2003. Part of what I love about this is that if ever there were Olympic Games for algorithms that compute pi, this one would have to win medals both for being the most elegant and for being the most comically inefficient. I mean, think about the actual algorithm here. Step 1, implement a physics engine. Step 2, choose the number of digits d of pi that you'd like to compute. Step 3, set the mass of one of the blocks to be 100 to the power d minus 1, then send it traveling on a frictionless surface towards a block of mass 1. And step 4, count all of the collisions. So, for example, to calculate only 20 digits of pi, which fits so cleanly on the screen, one block would have to have 100 billion times the mass of the other, which, if that small block was 1 kilogram, means the big one has a mass about 10 times that of the supermassive black hole at the center of the Milky Way. That means you would need to count about 31 billion collisions, and at one point in this virtual process, the frequency of clacks would be around 100 billion clacks per second. So let's just say that you would need very good numerical precision to get this working accurately, and it would take a very long time for the algorithm to complete. I'll emphasize again that this process is way over-idealized, quickly departing from anything that could possibly happen in real physics. But of course, you all know this is not interesting because of its potential as an actual pi computing algorithm, or as a pragmatic physics demonstration. It's mind-boggling because why on earth would pi show up here? And it's in such a weird way, too. Its decimal digits are counting something, but usually pi shows up when its precise value is describing something continuous. I will show you why this is true. Where there is pi, there is a hidden circle, and in this case, that hidden circle comes from the conservation of energy. In fact, you're going to see 2 separate methods, which are each as stunning and surprising as the fact itself. Delaying gratification, though, I will make you wait until the next video to see what's going on. In the meantime, I highly encourage you to take a stab at it yourself, and be social about it. It's a hard puzzle, so it never hurts to recruit some other smart minds to the task. You know that feeling you get when you have 2 mirrors facing each other, and it gives the illusion of there being an infinite tunnel of rooms? Or if they're at an angle with each other, it makes what's going on, where if the comes in from the right, lots of clacks, the total number of clacks looks like pi, and we want to know why. Here, we see one more perspective explaining what's going on, where if the connection to pi wasn't surprising enough, we add one more unexpected connection to optics. But we're doing more than just answering the same question twice. This alternate solution gives a much richer understanding of the whole setup, and it makes it easier to answer other questions. And fun side note, it happens to be core to how I coded the accurate simulations.
Third part. Wait, am I dumb? This is the new one, right?
In 2019, I put out a video about how 2 colliding blocks can compute pi. It's very fun, very surprising, and if you include the adaptations into shorts that I've posted since then, it is the most popular thing that I've put on the internet, and by a pretty wide margin. This year for Pi Day, I want to revisit this topic because there's actually a lot that I never talked about in the original video, including a fact that I didn't know when I first posted it and which I suspect no one in the world knew, which is how this is all secretly connected to quantum computing, more specifically something known as Grover's algorithm for search. Also, the whole crowd pleaser is that this is connected to pi, but very technically speaking, that full connection to pi is an unsolved problem. I'll explain what I mean at the end here. Just to recap, in case you haven't seen it, the setup of that original video was to have two blocks on a frictionless plane. At the very beginning, the one on the left is stationary, and we'll think of it as smaller, maybe 1 kilogram, and the block on the right is coming in with some speed. The two blocks bounce off of each other, there's a wall to their left, and the puzzle is to figure out how many total collisions would take place, including the collisions with that wall. So for example, in the smallest case, where both blocks have the same mass, with each collision, all of the momentum gets transferred from one block to the other, and including that one clack against the wall, the final count is 3. If that right block is bigger, maybe 100 kilograms, it means it has a lot more momentum when it's coming in, so it takes a lot more collisions to fully redirect that momentum. In this case, with the mass ratio 100 to 1, the total number of collisions is 31. For an even bigger mass ratio, let's say 10,000 to 1, that little block ends up getting really crammed up against the wall, and almost all of the collisions happen in this rapid burst right in the middle. In this case, it takes over 300 in total to turn that big block around, and after a nice long pause, as if the universe has a strong taste for drama, we see that the exact answer rolls in at 314, a number with eerily familiar digits. I do want to highlight a couple unrealistic things about this puzzle, the kind of nuances you can't fit into a short. When this big mass is growing, that burst of collisions in the middle just gets more and more concentrated. So in order to get the delightful result here, we have to make a number of idealizing assumptions. One assumption is that no energy is lost in the collisions. Physicists would call those perfectly elastic collisions, and the astute viewers would then be raising their hands and complaining, well, hang on, shouldn't that mean that we don't hear completely? But we're going to be ignoring
Fuck this. Dude, classical mechanics is so. Okay, so we have the club, which is, let's say, 0.2 kilograms, and then we have the block, which is 0.045 kilograms. Okay, this is moving at a velocity of 4.4 meters per second. It's like, why is it doing all of this, man? This is the problem with when you give it code. Okay, wait. I need to learn about perfectly elastic collisions between two bodies on a frictionless surface. And I just don't know any of the math. And I want to know how we can derive. Let's say one of the blocks or one of the masses is stationary at the start and the other one is not. How do we figure out how the system evolves? See, if you ask it like plain context, it's going to be way better. It's not going to like start throwing me code and like a whole bunch of stuff that I don't even know about. So I guess from a review from yesterday is that mass times velocity is equal to kilogram meters per second. Okay, so before collision, the total momentum is so. Okay. So this is the conserve of momentum equation. Okay, and then the second part is going to be okay. Okay, so the full system